use my 15 minutes of fame to talk a little bit about random series and some of the properties. So the titles talk about Rademacher Fourier series, but let's start with random Taylor series. So these are really simple objects. So I look at the infinite sum, a(n) psi n z to the n, where psi n's are my independent random coefficients, and a(n) are some deterministic non-random coefficients. So you can assume all kinds of stuff on the psi n's. I will always assume that the expectation a0 and that the variance of that is 1. So in general, they can be complex. And it turns out that the coefficients a(n) determines the radius of convergence of this series. So almost surely the radius of convergence is given by the usual formula that we know. And we can ask all kinds of questions about the behavior of these functions, and separate related questions will be about random Fourier series. And it's clear that those two are related. So there are, let's say, 3 classical choices for these random coefficients. So the G, these are the complex Gaussians. So usually questions about Gaussians are the simplest, as you know. And there are questions about, for historical reasons, Steinhaus coefficients are just uniformly distributed over the unit disk. And finally, there are questions about Rademacher coefficients. So this shall just take the values plus minus 1s with equal probability. And usually the Rademacher coefficients are the most difficult ones. And sometimes even one can reduce questions about general coefficients, or at least general symmetric coefficients, to the Rademacher case. So I will just give 3 classical types of problems. Or questions that people ask. So the first one, and historically probably the first, is about the natural boundary. Of a random Taylor series. So here the question is, let's say that the radius of convergence is 1. And we want to show that almost surely we cannot extend our random function beyond the domain of convergence, the unit disk. So first, Borel asks this question. So there was not a probability theory at the end of the 19th century, so he asked it in non-formal way. And then Steinhaus first proved it in the end of the 90s for his random coefficients. And then Paley and Zygmunt proved it for the Rademacher coefficient, beginning of the 30s. So another kind of question is, let's say, behavior of boundary values. Or convergence of Fourier series. So here are the kind of questions that we ask. We look on this random kind of Fourier series and we ask, does it converge depending on the properties of the sequence AN, if it converges in LP sense, if it converges almost surely, if it converges to a bounded function, to a continuous function, all kinds of these questions. So again, Paley and Zygmunt proved the classical results in the 30s, and then there was results of Billard and some Marcus and Pizier. Until the 70s, people proved all kinds of questions about the boundary values, but those two I won't remark on them anymore. So the third kind of question is about the range of Taylor series. So we look again on the case where the radius of convergence is 1. So these are our series F is determines almost surely a random an analytic function in the unit disk, and we want to look at on the range of this function. So to make the question interesting, we require that the sum of squares of the coefficients diverge, and then we ask if it's true that almost surely the range of F is equal to the whole complex plane. So I'm not exactly sure on the exact details of the history of this problem. I think that Zygmunt already asked kind of related questions. So it appears in a famous book of Kahan about random series. And what was previously known, so Offord in the 70s solved the case of Steinhaus and Gaussian. And basically any case where you have a density. And the Rademacher case was open, so there were previous results under some additional assumptions. So now, I just want to relate quickly the result. So quickly relate these two logarithmic integrability in the titles, and then I will just say what we managed to prove. Yes?
Are all these results really easy, or easy to see if, let's say, all the AIs are 1? Just for intuition.
If you have the stronger conditions, you have regularity conditions, you have all the coefficients ANs, then you can prove it is easy to prove the result. Okay. If you, for example, I think that the result is true for Rademacher case, or it was known to be true if the lim inf of the AN is positive or something like that. Okay. Even
very simple case when they're all 1s, maybe we should be able to see.
So it's probably even easier. Yes.
Even easier.
Yes.
Yeah. That's
Yes.
right.
Yes. Okay. Okay. So we want to count zeros of entire functions. So basic methods that we count by NR the number of solutions of the equations f of z in the disk of radius r. And then we have an integrated zero function which I denote by capital N of R. So we have famously Jensen's formula, which relates the number of zeros to the logarithm of the function. Okay. So for example, if you want to calculate the expectation of this function, then it is more or less the expectation of the logarithm of f capital of R. Okay? And the thing is that this works for Gaussian coefficients. We can exchange the order of the expectation and the integrals, then we can calculate the expectation pointwise, and we have an estimate for an R. Once we have an estimate for an R, we can also get an estimate for n of R. So I will call this differentiation. It's not exactly that. So in particular, we can prove that even find the rate of growth of the expectation. So this is still not give us, it still won't give us the solution to this problem, because here we want something almost surely for all the values. Okay? But we can similarly define a counting function for the b values of f and relate it using a similar formula to the logarithm of f. So it turns out that this result can be reduced to questions about the logarithmic integrability. Since I don't have too much time, you have to believe me. So this question can be reduced to a question about the logarithmic integrability of Fourier series. So our main theorem here, so first of all, before that, the problem here is that we cannot do this this exchange of integral of an expectation for Rademacher series. Okay, so some other ID should be used. And for Rademacher, we just notice that we can calculate the expectation by calculating the expectation of the integral. Okay, so here we want to exactly calculate the expectation of the integral without changing the orders. So our theorem, and by R I mean together with Misha Sodin and Fedor Nazarov. Is that for any p and any series g theta with psi n Rademacher coefficients, and I assume some normalizations that the sum of the coefficients is 1. We have that the integral of the logarithm to the power p is bounded by some constants that only depends on p. And since I don't have enough time, I'll just say that a generalization of the theorem gives a positive answer for the case of Rademacher coefficients without making any assumptions on the sequence AN. So I don't need any additional regularity assumptions. That's the sum of them diverge in the original formulation. And it also gives a lot of information about the distribution of the zeros of entire function. In particular, it allows to generalize classical results of Littlewood of Offord to show that the zeros are equidistributed and gives a good error terms on the equidistribution and so forth. So I think I'll stop here. Thank you.